Good morning, everybody. Welcome to this episode of the Terahertz Talks series. Today, I would like to discuss examples of integrated semiconductor circuits as well as the systems around them, and finally show some experimental setups and results. So I want to put this into the context of joint communication and sensing, since this is a highly relevant research topic and that drew a lot of attention recently. So with that, let me quickly outline my talk. First of all, I want to give you a quick introduction to joint communication and sensing, talk a little bit about concepts available right now that have been presented by our colleagues, Thomas Dahlmann, for example. Then I will move on to show you a video demonstration by Till Ziegler-Bellenberg, who wants to present his work at 300 gigahertz, a joint communication and sensing demo. Then I will talk a little bit about the details of mainly his work at 300 gigahertz, followed by a different concept, the harmonic radar approach, that is first of all demonstrated by Steffen Hansen in his video. And finally, I will discuss the details about the harmonic radar and conclude my talk. So let's start with the introduction. The idea of JCS is around for a couple of years now, and the main driver for it, in my view, is to use the same radio for radar and communication and radar sensing, for example. One approach is to share the frequency spectrum via orthogonal waveforms or use it jointly with the same waveform. So with a limited frequency spectrum around, this means we have a competitive resource exploitation. And the shown concept over here enables coordination and localization with the same device or through a particular service. So as mobile and radar technologies have historically developed independently, now the convergence of these technologies is becoming increasingly feasible and beneficially, especially with this high bandwidth that is available in the millimeter wave spectrum, and also along with the devices that are available, for example, the software-defined radios. Furthermore, radar sensors can utilize the resources provided by the mobile network operators, MNOs, and they can use the signals to operate more efficiently. The integration allows base stations to serve dual roles as radar illuminators, while mobile devices can act as local sensors, facilitating real-time data collection and processing. So the merging both technologies brings many new applications, and a couple of those I would like to discuss on the next slide. So the joint design of communication and radar systems presents unique opportunities for enhanced performance and resource optimization. And as JCS continues to develop, it holds promise as a transformative approach for various applications, from autonomous vehicles, saying that we need connected vehicles, and all the way up to advanced air traffic management, for example. Another key application is the industrial automation, which can benefit from JCS. So just think of collaborative robotics, human-machine interaction, and asset tracking in factories, for example. The traffic management in cities can increase public safety and allows for much better navigation capabilities of our mobile devices, for example. And last but not least, we have benefits in the health monitoring sector that provides contactless vital sign monitoring and further healthcare applications, along with identification of patients, for example. So within the 6G community, there's often consensus that future systems capable of both communicating and detecting objects will be based on communication circuits. And they do that because they want to circumvent problems such as licensing and production volumes, for example. They have it in the communication chips. At the same time, they see a wide range of applications on private and industrial premises, where easily a radar system can also be set up. So sometimes in these applications, it's much more important to have a high resolution in the radar detection than it can be provided by a communication device. And this is one reason why we further pursue our road using radars with communication functionality. And with that being said, I would like now to move on to the first hardware example of this talk, which is the 300 gigahertz system for joint communication and sensing presented by Till. The design and the experiments have been conducted by him, and I will move on to the video demo right now.
This is our fully integrated 300 gigahertz joint communication and sensing system. It can either serve as a standalone ultra-wideband radar sensor or as a RF front end that can upconvert and downconvert arbitrary IF signals. The system is made up of two cost-effective FR4 PCBs that handle the frequency stabilization, general control, and the radar IF. At the heart of the system lies this custom Siege MMIC. It handles all high frequencies, generates the terahertz signal, and radiates them using its on-chip patch antennas. To extend the range of the system, we focus the radiation from the on-chip antennas using a polypropylene lens. Now we are using our module as an FMCW radar sensor. With FMCW trips from 340 GHz to 240 GHz, we are trying to detect this metal plate using this radar sensor. On the screen you see the IF signal recorded by the module's ADC, as well as the range profile calculated from that. This peak corresponds to the metal plate. The extreme bandwidth of the system is useful for thickness measurements, as the bandwidth is directly linked to the range resolution of the system. To separate the interfaces of this 3.4 millimeter thick plastic disc, you would need a bandwidth of at least 44 GHz. And when this disc is placed in the sample holder, we can separate the front and back interface in the processed IF data. Now for the second use of this module as an RF front end. When used as a transmitter, an external IF of up to 7 GHz gets upconverted to the terahertz region and radiated. Terahertz signals received by the system get downconverted and output to this mini SMP socket. To show this, we use these SDR modules to generate a digital signal modulated onto a 500 MHz carrier. This IF signal is routed into one of our modules and upconverted with 300 GHz to the terahertz region and radiated. The radiated signal is received by the second module, which downconverts it by 302 GHz. The resulting IF of around 2.5 GHz is received and downconverted by this second SDR module. On the top of this screen, you see the series of ones and zeros transmitted over terahertz, generated by this SDR and received by this SDR.
All right. So, and since Till is also present in the audience, many thanks for that, Till. And now that we have seen this impressive results, I would like to talk a little bit about the motivation for this work and subsequently go a little bit into more detail about the system that he has built. Okay, so the bandwidth is the key metric enabling high range resolution in communication, and in communication circuits, high data rate. So achieving a bandwidth of around, let's say, 50 to 100 gigahertz is very tricky at lower frequencies, since relative tuning range is a decisive factor here. There are also optical systems, but we are approaching this from the different direction of the spectrum. So hence, for our perspective, going up in frequency is one way to go. There are some key industrial applications that require very high range resolutions. And in the top right pictures over here, there are 3 examples. So the first one is a hot rolling mill example where the width of the rolled metal sheet is detected. The second one here in the middle is where we want to detect the thickness and the ovality of the plastic pipes that is running at a customer of ours. And last but not least, we want to do defect detection in fiber composites. For example, these fibers are used in wind turbine blades, and the defect is crucial to be detected, and it has to be detected within an intransparent fiber composite. So here we are using polarimetric radar. Besides the bandwidth, we need a compact system and a robust system that also works in harsh environments. And in total, that's the reason why we decided to build a JCS device at 300 gigahertz in the J band. So let me show you now a micrograph of the MMIC that has been developed on the next slide. The chip that is visible over here has a size of 2.7 and 1.3 millimeters and is fabricated in Infineon's B12 HFC technology, which is a 90 nanometer BiCMOS process that includes high-speed heterojunction bipolar transistors, HBTs, with an FT max of 300 gigahertz and 600 gigahertz, respectively. So those transistors enable circuits in the millimeter wave to terahertz domain, but we have to keep in mind that we are very close or even higher than the transit frequency at this point, so we don't have any current gain. And this already indicates that there's finally the need for further methods outside the chip to increase or focusing power to maximize the achievable range that we are targeting here. So marked on this chip photo, there are 3 blocks: the RX pass, the TX pass, and the LO generation block. And these blocks I like to dive into a little bit on the following slides. Finally, I will talk about the complete system setup. So first of all, I would like to show you a complete simplified block diagram of the 300 gigahertz transceiver circuit. So on the right side, in the middle of it, there's the heart of it, this silicon germanium MMIC with the receive path and the transmit path over here, along with the front end board in the lighter gray area, or in the darker gray area, and the back end board shown here in the even darker gray area. So the LO generation is happening on the back end together with the front end PCB, which is stabilizing the on-chip VCO, where we have a divide by 8 circuit to have lower frequencies interfacing between the MMIC and the front end PCB. There are on-chip antennas, which are really needed at 300 gigahertz because you don't want to have any bond wires between the MMIC and the antennas. So yeah, since we use this on-chip antennas, there are almost no high frequency interfaces from the chip to the PCB, so they are all below 10 gigahertz. On this slide, I want to dive a little bit further into the key components and the functionality. So on the left side, there is the LO generation block. It consists of an E-band VCO, which features an extremely high tuning range and is covering the almost entire E-band from 60 to 90 gigahertz. The VCO is stabilized by using a PLL integrated on the front end PCB, and it needs a divide by 8 prescaler, which is set up by a static divide by 8 chain to work with off-the-shelf components, which work around 10 gigahertz on a PCB. We are using a commercial ADF 4169 fractional N frequency synthesizer chip in conjunction with an active loop filter. The LO generation is achieved at quarter the frequency, so there's a need for a frequency doubler right here. Right here in this side, followed by the Wilkinson divider to provide 2 LO signals in the D band, one for the RX and one for the TX chain. So on the right side, there's a simplified block diagram of the RX path, and the signal that is received by the antenna, with the on-chip antenna, needs to be down converted, which is done by a Gilbert cell-based receive mixer. And for that to work, we need to convert the single-ended D-band LO that has been generated over here to a differential J-band LO. So These circuits are meant to do that. So we end up with a differential 300 gigahertz LO that is driving this or serving this mixer as an LO. The IF here is routed off chip, and it can take one of two routes. Two operation modes. First option, the signal is filtered and subsequently amplified and digitized. This is for the radar operation. And second, if the signal is routed to a coaxial cable connector to a USRP device, for example, and in this option, we build a super hetero receiver with the SDR. This is more straightforward, but to upconvert the IF to the J-band, there we use a more advanced approach, which I want to discuss on the next slide. So the transmit path is displayed schematically in the sketch over here, and the mixing is done in two stages. Both of the mixers use a D-band LO, similar to a subharmonic approach. The problem is the LO power. So in the J-band, the LO power would not be sufficient to drive the mixer. So the approach here is to generate high power of the LO in the D-band. Okay, so let's move on to the radar case. Here the signal, the J-band LO signal needs to be radiated. Switching between radar and communication mode can be done using the first mixer stage. But to understand how this works, I would like to show you the circuit topology on the next slide. So both of the mixers are Gilbert cells, as I mentioned, and the schematic here shows the architecture. Both mixers are more or less identical, but they have different matching and a different biasing network. So the red highlighted MOS transistors are only present in the first mixing stage. And if they are activated, they shift the bias of the differential pair. So either LO feed-through gets maximized, then we have the radar operation, or we can put through the IF input so that the IF is modulated onto the LO signal. This we need for the communication case. So that is the main feature making this MMIC hybrid component that serves both radar and communication functionality. And with that, I would like now to move on to the integration, the system integration of the MMIC and the PCBs. So the 300 gigahertz system is made up of a compact stack of 3 FR4 printed circuit boards, short PCBs, and they are mounted inside a 3D printed housing. The MMIC itself is glued and bonded directly to one side of the front-end PCB, and on the other side of the same board, the PLL for frequency stabilization, IF filtering and amplification for the radar mode, and sockets to connect modulated IF signal for the communication mode are integrated. The second PCB serves as a breakout board and an adapter to the third PCB, which is the applied radar backend. This backend module houses further IF amplification and filtering, as well as the analog to digital conversion, the ADC, a reference crystal oscillator, a power supply powered from a USB port, and a microcontroller. And to enhance the range of the system, a focusing elliptical PTFE lens can be mounted to the housing or not, depending on the application that is targeted. So before I show you the measurement results that have been gained with the described system, I'd like to discuss a little bit the calibration procedure that was used for that. So to extract the results, it was necessary to calculate the transfer function of the system from a reference measurement using a known target. With a known response x of the target, we can multiply that equation over here, y equals h times x, sorry about that. We can multiply that from the right with the inverse function of x to obtain the transfer function h. The plot on the right displays the normalized transfer function in orange and the IF amplitude in blue. So, and to plot the the plot on the right shows the measured IF response and of a target that we really measured. So this is the real measurements. And finally, the H function was extracted by using that. And using that procedure, the following results have been obtained that are shown on the next slide. Here, the radar was operated in FMCW mode, running a downchirp from 330 gigahertz to 240 gigahertz. A tuning range of 90 gigahertz was used here. And in this experiment, a metal plate was used as a target, and the calibration method from before was applied. The graph shows the calibrated and the uncalibrated curve, and it demonstrates that the range resolution is much higher after calibration because you can see the peak is much slimmer than before. The theoretical maximum resolution for a 90 gigahertz bandwidth is 1.67 millimeters and derived from the 6 dB peak width of 1.97 millimeters. We achieved an effective bandwidth of about 76 gigahertz. The communication functionality was already demonstrated by Till in his video, where he brought the bit stream from one to the other device to a stop by blocking the signal with his hand. And with that, I'd like to move on to the second MMIC example for joint communication and sensing. The second example is based on the harmonic radar principle, where the illumination of the target with an active tag happens at the fundamental frequency, which is doubled and retransmitted by the tag so that the reader device can evaluate the harmonic frequency and ignore all the other reflections from other objects by filtering out the fundamental frequency. So it makes it not prone to clutter in very crowded environments, for example. But this work was done by Steffen Hansen. He has designed it for both radar and communication functionality, and he will give you now a quick demo of his work in the following video.
Thank you, Jan, and hello also from my side. In this short demonstration, I'll present our harmonic transceiver and highlight its core functionalities. The system is built around a custom-designed FMCW transceiver MMIC in silicon germanium technology. Above the transceiver, you can see the tag. It also integrates a MMIC which reflects the signal on the doubled frequency. It uses differential patch antennas combined with integrated waveguide antennas. The transceiver transmits in the 61 GHz ISM band. A tag receives this signal, amplifies it, and performs frequency doubling. The signal is then retransmitted in the 122 GHz ISM band. The reflected signal is then down-converted to the intermediate frequency. Connected to the tag is a microcontroller, which provides dynamic control over the tag's behavior. It allows modulation of the backscattered signal, either amplitude only or amplitude and phase, depending on the tag. This modulation enables several features: individual tag identification, separation of multiple tags even when they are at the same distance, and communication between the tag and the reader. Now, let's look at a short video example using our harmonic radar system with two active tags. This scene focuses on demonstrating the separation capability of the active tags by modulation. In a second window, two graphs are shown. One displays the frequency spectrum after FFT processing of the received signal. The other shows the last 30 measured tag distances over time. Both tags are placed approximately 3 meters from the radar and intentionally positioned at the same distance. The active tag design results in a strong radar echo, which enables highly stable distance measurements better than 1 millimeter. When the tags are moved, the measured distances change accordingly. Each tag applies a modulation to the reflected radar signal. This modulation enables separation of the tags. This demonstration shows just one example of how active tags can be used. Next, Jan will demonstrate how we can use this hardware in the context of joint communication and sensing. Thank you, Jan, and hello also from.
Okay, yeah. So Steffen is not here, so I cannot thank him, but I'm very grateful for his video. And to give you more insights into the harmonic radar and its JCS features, I will present some of the relevant details of the setup and the different modes of operation that are possible with this. So the harmonic radar principle is based on tags as radar targets that reflect a harmonic frequency from a clearly defined position. So from a circuit perspective, the most straightforward implementation is the frequency doubling. That's what we have done here with the tag. Thus, the harmonic radar is a cooperative radar. The tag consists of an antenna to receive the radar signal from the transceiver and send it back after frequency doubling via a nonlinear element. And the tag is therefore illuminated at the fundamental frequency and reflects at the harmonic frequency. So with the receiver operating at the harmonic frequency using a frequency doubler in the LO path, the intended radar response of the tag can be coherently down converted, which is an important aspect, to the intermediate frequency IF. The FMCW principle, where the distance to the target is determined by the time, delay, and the ramp slope, remains the same, but with the difference that the ramp is evaluated at the harmonic frequency, which also means that the bandwidth is doubled. And the reflections stemming from unwanted objects, unintended objects in the environment, which reflect at the fundamental frequency, they can effectively be filtered out. To use this principle in highly complex scenarios, two properties are very essential. The radar response from the tag at the harmonic frequency must be sufficiently strong, and unintended reflections, they must not appear in the IF spectrum. Otherwise, we can not filter them out. So on the next slide, I will show an experiment where the range of the device was in the focus and was investigated. The experiment, which was set up to demonstrate the range capabilities, is shown on this slide, and the tag was mounted on a linear rail with a maximum distance of 45 meters. That was a limit coming from the site where we did the measurements, or where Steffen did the measurements, and the radar system was built to switch antennas and plug them to a waveguide port. So we can connect different kind of antennas for a certain purpose. And in this case, we wanted to have high gain, so we used horn antennas for high ranges. And the results show the normalized amplitude, so at the bottom right, versus distance. And there's a strong radar reflection with an SNR above 70 dB. The range resolution was 1.16 centimeter, what is also indicated by the peak width, and which correlates to the bandwidth that was used in this experiment. The solid line indicates the measurements with a tag that is still driven into saturation by the illumination coming from the radar device. At a certain distance, the cross point between the dashed line and the solid line, the input power is not sufficiently high enough to drive the tag into saturation. And that changes the characteristics of the amplitude versus distance. And it suddenly is proportional to 1 divided by r to the power of 6 instead of 2. So it drops much faster. This experiment already shows that a very high amplification is required to achieve reasonable ranges, and therefore different versions of the tag device were designed for different applications. So on the next slide, I want to show you one version of those tags, which is called our conversion high gain tag. And it features a chain of 6 amplifier stages at 60 gigahertz at the input of the tag, It has a high preamplification, which is required due to radar equation of harmonic radar, where the amplitude drops with 1 divided by r to the power of 6, and overall inefficient power transfer due to very high free space path loss at millimeter waves. The differential design for even order harmonic suppression is also key to this design. So especially at fundamental frequency, especially at fundamental leakage, at output suppressed to reduce the risk of instability. So this is one big advantage here. We have the feedback is done when there is some feedback coming from the antenna to the input. It is transmitted at the harmonic frequency, and this does not make the circuit unstable, at least not as quickly as the feedback at the fundamental frequency. Okay, so what was achieved with this? There is a high conversion gain of bigger than 47 dB from 57 to 64 gigahertz. There's a current consumption of 45 milliamps, and this is true for 100% duty cycle. So we don't have to run it in on state all the time. So there's high potential for the reduction of power consumption. The presented hardware that has been used for those experiments and further variants and further variants of it can be operated in different modes. And this is I would like to show you and discuss on the next slides. So there are 3 modes visible here: the radar mode, simple radar mode, backscattering mode, and AM/PM mode. In all cases, the carrier is transmitted by a transceiver, and in 2 of the cases, it is modulated on TEC, so that a correlated received signal can be demodulated from the transceiver. So I just want to point out that this brings the advantage that there's no further carrier required in this circuit. So here in the radar mode, the signals already indicate that this is, first of all, the harmonic radar approach, but in an FMCW fashion for the ranging of a particular device or a particular target. In the backscattering mode, we have a continuous signal sent to the target, to the TEC, and here the modulation happens at the output variable gain amplifier. So we can perform ASK or OOK modulation of the TEC. This already has been enabled by the radar hardware. And then we have a third mode, which we call the AM/PM mode for amplitude modulation and phase modulation, where the TEC additionally contains this mixer, which can be used to do either amplitude or phase modulation. Send it back, it can be demodulated by this mixer of the receiving device, or we call it the reading device. So an example using the radar mode, I would like to explain in the following slide, where we used it for 3D sensing. So here you can see a distributed sensor network using a TEC cube and 4 harmonic radar sensors. So the advantage of using radar is that it is insensitive to dust, fog, and smoke, as you already know, and this makes it a perfect candidate to work in an industrial surrounding, for example. The concept is sketched in this figure on the left side. As I mentioned, we have 4 harmonic radars and 1 TEC cube in the middle. The photo on the right shows the positioning of the devices on the XY scanner that was used for moving the radar cube. And after measuring the response of 4 readers, the positioning of the cube was determined by the concept of multilateration, and this led to the accuracy plots over here, or the error plots over here, with a maximum error of an average error in the X direction of 0.89 millimeter, in Y direction of 0.57, and in that direction it was a little higher, which stems from the positioning of the devices relatively to each other of 5 millimeters. So if you have a 2D plot here, you achieve a ranging with an error less than 1 millimeter. And to further demonstrate the communication capabilities of the harmonic radar system, I would like to discuss the backscattering operation mode on this slide. So in this simulations-based experiment, the signal that is received by the tech, so the illumination signal, is amplified, doubled in frequency. This is the normal harmonic radar functionality, and finally modulated by changing the gain of the final gain stage over here. So yeah, this is an example of the general communication using the backscattering feature of the presented hardware. So in the simulation results, the received 60 gigahertz signal was at minus 60 dBm, amplified, converted to 120 gigahertz with 67 dB conversion gain, and the output stage gave the modulated signal at 120 gigahertz. The timing corresponds roughly to a modulation signal in the 4 gigahertz region. And so we have a coherent signal with on-off keying modulation that is retransmitted to the reader. I have another example, and that example shall highlight the feature of using communication for device identification. So what is the motivation for this work? So one thing why you could use text as a reference point on the ground for drones, for example, is precision landing assistance in dense GPS degraded environments, for example. So it can be something like assisted takeoff and landing, as it is called. Further aspect is that radar systems can be used for vital sign detection, for example, in emergency scenarios. So the signals that must be detected and processed are usually very weak and need a sensitive receiving device. Additionally, the drone motion causes interference in a linear radar-based chest movement detection. So we have cluttered environments, and they amplify this effect even further, reducing live detection reliability. So here the tags, they serve as the fixed reference markers in the scene. So allowing the harmonic radar to do some ego motion compensation, or on-chip compensation is also called sometimes. So, and this scenario enables correction of drone-induced motion artifacts in radar, so that airborne vital sign detection becomes feasible. A second showcase using the harmonic radar for communication was already presented by Steffen in his video, and that brings me already to the conclusion of my talk. So in this presentation, I discussed different advantages of devices featuring sensing and communication. And to provide insights into our approach to joint communication and sensing, I included MMICs and also the systems around them, in particular the two examples. And they were first demonstrated in short videos by Till and Steffen, and followed by a discussion of the relevant details about the circuit topologies and systems which they are integrated into. And to draw a conclusion, I would like to say that the radar-centric joint communication and sensing approach opens up the field to many new applications, and there are still many left to be discovered. And with that, I'd like to thank you for joining this talk.